Hello everyone, so here's me doing another video on math, this time 2015 question 3. This one, it's got good points and bad points. Some bits of it are really very straightforward, but you know, when you look at the whole question, this is all of it, like, you know, it's got a bit of cognitive load to it, as in like you've got to bring in lots of parts from earlier in the question. You end up getting lost in like the long kind of like discussion of the question. It's the complete opposite of this kind of question where it's all very short and cute, and you know, you've got to figure it out for yourself. This is trying to give you a lot more kind of like scaffolding to achieve what they're trying to do, but yeah, that can actually sometimes confuse people more. Anyway, let's just jump into it. So we've got basically this idea that an excellent approximation of a function to another function, just from 0 to a half actually as well, is going to be where the two functions differ by 1 over 320 or smaller. And a good approximation is where the two functions differ by 1 over 100 or smaller. And so, as they point out, all excellent approximations will be good approximations, but not all good approximations will be close enough to be excellent approximations. And that seems pretty obvious to me. I don't know why they make such a fuss of saying it at the start. But yeah, the first two parts are really quite straightforward because give an example of two functions f and g such that f is a good approximation to g, but f is not an excellent approximation to g. Well, I mean, the one I came up with, and I'm sure we all got different ones here because you literally can do anything. I just thought, well, if f of x is x plus 1 over 101, then certainly if I make g of x, like f of x is always 1 over 101. That's the difference between f of x and g of x. And because they're linear functions, obviously, one's a y equals x, and the other one's like y equals x plus a bit, you know, like 1 over 101 there on the y-axis. They're always going to have the same difference in the y coordinates, which is what we're really finding here, the difference in the y coordinates, and that difference will be 1 over 101, because if you subtract the functions, you get 1 over 101. Obviously, that's slightly smaller than 1 over 100, like, which is good, which makes it a good approximation, but it's not an excellent approximation. Now, I did have a look at the mark scheme when I went over my answers to this question, and I noticed that they said, oh yeah, obviously you could have just f of x is like, you know, 0 essentially, and g of x is 1 over 101. There's no need for an x there, is there? You know, that's like the really boring case if you ask me, the really trivial case. So they did point out you can have almost anything there, like you really can. It's just got to hold from 0 to a half, remember. So, you know, if you were going to do some non-linear functions and it was a bit more interesting, well, you know, more power to you. But I just went straight for the easiest answer, which seemed like the linear function I was doing. Okay, what I did find though was that my answer was really instructive just by pure chance for when I looked at the next question. Whereas f of x is x, g of x is x plus sine of stuff over 400. Well, you know, before I actually write down what I'm going to do to justify my answer here, I'm just going to point out, you know, for exactly the same reason as this is obvious, yeah? When you subtract, the x's are going to cancel. In other words, the difference is sine of 4x squared over 400. Now, why would this be an excellent approximation? Well, it's because sine of a square, well, yeah, sine of anything, sine of stuff, is always trapped, whatever the stuff is, between -1 and 1. Yeah. So, you know, the 4x squared is really just a distraction. It really is here. And you can just, in fact, I might start my argument by pointing out -1 is less than or equal to sine of anything, but we'll write the 4x squared, which is less than or equal to 1. Yeah. Sine's basically always trapped between -1 and 1. And so divide that by 400, and you've got that fact over 400 is less than or equal to 1 over 400. We've got to justify it, haven't we, and really show the examiner we know what we're talking about. Hence, the modulus of f of x minus g of x, well, that's going to be, when we subtract, you know, the x's are going to cancel, and we're going to end up with the modulus of sine of 4x squared over 400. Now, I'm sure you know that one way of writing, you know, if you've got -1 is less than x is less than 1, another way of writing that is mod of x is less than 1. Yeah, that's just they're absolutely equivalent. And you should understand why as well. It's because we're taking the absolute value of x, we're immediately making it positive. So the absolute value of x is less than 1. So this is exactly the same as what I've got up here. Like, we're essentially saying here, well, that means that this is definitely less than or equal to 1 over 400. Yeah, and that's by like the reverse of going from here to here, if you see what I mean, going from the modulus back to the inequality. We've already shown that that's the case. Hence, you know, f of x is an hence f is an excellent approximation. I suppose I should point out that that is less than, not or equal to, but less than 1 over 320. Hence f is an excellent approximation to g. My main concern on these kind of questions would be I'm not writing enough down to get full marks. What makes that doubly difficult is you never know how many marks a part is worth in these extension papers, which makes it so frustrating. I honestly do not know a good reason why they don't tell you how many marks something is worth. It at least gives you, as a student, an idea of how much explanation they want. Here, I think they would have settled for very, very little. I'm just glancing on my other monitor of what they actually had down in the mark scheme. I can't remember now, but let's actually have a quick look. Let's just go into it. Yeah, they didn't write much. Like it was all done on one line, and it was very similar to this kind of setup. So yeah, there we go. So part 1 and part 2. I mean, what's annoying about that is you can almost just kind of see it in your head, can't you? Like sine of stuff's trapped between -1 and 1. Divide it by 400. It's definitely going to be within 1 over 320. Okay, next part. Okay, they then basically say we're going to try and find a good approximation to the exponential function. This is definitely describing a function which integrates to itself. You need the 1 plus because I don't know if you're familiar with the Maclaurin's series expansion for e to the x, but it goes 1 plus x. It's essentially the f of x here. But you're not allowed to use this fact, yeah? This is what e to the x really is, if you like. It's a power series expansion. Goes on forever. And so if you integrate this, it integrates to x plus x squared over 2 plus x cubed. It integrates to itself, but you're missing the 1 plus, and that's why you need the 1 plus at the start. So yeah, that's just gonna, that's why that looks like that. But yeah, so they're basically saying we're going to try and find a function which integrates to 1 plus itself. They're basically telling you the plus c in the integration, but they're giving it definite limits. Okay, so yeah, I'm starting to waffle on now, so let's avoid that. So we're given this cryptic h of x, and we're also told that f of x is the first 4 terms of the Maclaurin's expansion for e to the x, but you're not allowed to use any knowledge you've got of e to the x, so fair enough. They do that a lot actually in these papers. Okay, part 3, show that if g of x equals 1 plus between 0 and x, f of t dt, then f is an excellent approximation to g. Okay, my thinking here is as I'm given f of x, I might as well directly integrate it. So g of x is equal to 1 plus. Now I can integrate this. I often say, and I'm going to argue this in a second, that when you see integrals in the mat, they're really, really, really often not about integration. They're often about like finding areas under curves in some way. You're going to see that in a second on this question. So look out for that. But here, the one thing you are able to do in AS integration is integrate a polynomial. And so, yeah, we can integrate this. This isn't a problem. So we're going to get 1 plus, open brackets. Now, when we integrate that, we're going to get t plus t squared over 2 plus t cubed over 6 plus t to the 4 over 24 between x and 0. Naturally, that goes to x. All the zeros are going to cancel when you plug it in, so I'm only going to just replace t for x, basically. X squared over 2, x cubed over 6, and x to the 4 over 24. Yeah, and that's it, completely integrated. If you want to write down another set of brackets and do the minus zeros, be my guest, but that should be what g of x is. Now we're going to show that f is an excellent approximation to g. So let's just write down f next to it so we can see it nice and clear. Now to find these approximations, 1 plus x squared over 2 plus x cubed over 6. To test for whether these are good or excellent approximations, we need to subtract them and find the absolute value, the modulus, between them. So, that's the definition of an excellent approximation. Are we trying to show this is excellent or good? I can't remember. We're trying to show it's excellent. So we're going to show that when we subtract it and find it, make it positive, it should be less than or equal to 1 over 320. And it's only valid for 0 to a half, by the way, that's the way they've defined it. Now, you might notice straight away that g of x is larger than f of x because it's the same as f of x, but it's got one extra term. So I'm going to do bigger minus smaller to avoid any problems with negatives. So g of x minus f of x, clearly that's just going to equal, that's going to cancel, that's going to cancel, that's going to cancel, that's going to cancel. And so clearly it equals just a term on the end. And that's kind of good. Now, we've got to show now that this is definitely less than or equal to 1 over 320. Now, remember, we're only doing this for 0 is less than or equal to x, which is less than or equal to half. Yeah. Now, we want to show that this value is definitely less than 1 over 320 or equal to it, actually. Now, this is an increasing function. Yeah, you might want to just quickly make a note to the examiner. This is an increasing function. Now, why am I mentioning the fact that it's an increasing function? Well, it means I can just plug in x is a half to find the greatest value of that in that range. Because it's an increasing function, the bigger x number you choose, the bigger y coordinate you get, because the gradient is strictly positive whilst it's increasing. And so I can use x equals a half to find what the size of g of x is minus f of x, because that will be the largest value of g of x minus f of x. And I want to show that the largest value is still smaller than 1 over 320. Then g of a half minus f of a half, well, it's going to equal a half to the power of 4, which is a 16th. And then I'm dividing that by 24, which is the same as timesing by 1 over 24. That comes to, what does that come to? 240 plus 6 times 24, 240 plus 144 is 384, I think. Yeah, okay, and hence g of x minus f of x, the modulus of it, if you like, because that's what they use in the definition, is less than or equal to 1 over 384. This is clearly smaller than 1 over 320. I'm just justifying what I'm doing here. And I can say, so this is, so f is an excellent approximation to g. I think that's the way to put it. I'm surprised they use g for this function and g for the other one, which we just used. So yeah, hence f is an excellent approximation to g. The maths in this question does not feel like mega difficult. I'm sure when you see it, you're like, yeah, that doesn't look that hard, actually. You don't really feel like you're doing much maths in this kind of question. Some awkward stuff with inequalities at the end, I suppose. Okay, right, so that's that done. Part 4. Show that for x is greater than or equal to 0, this funny looking result is true. Well, let's have a look at it. We've got h, f's, and g's in this. G is what we defined it to be before. We've got g of x actually as that. I wish I hadn't crossed out the lines here. Let me see if I can just delete those so I can see what I'm doing. Okay, so that's g of x. It's nice to know what g of x is. And this is h of x minus f of x. So let's kind of do it. What side looks more complicated? When you're trying to prove something, it's nice to start with right hand side equals stuff equals stuff equals stuff equals left hand side or something like that. So that's what I'm going to do. I'm going to point out the right hand side, which is g of x minus f of x plus the integral from x to 0 h of t minus f of t. And I tell you what, I think I'm going to quickly write that out separately, because naturally you're always allowed to do that with integrals, provided the limits are the same here. You're allowed to combine them and take them away, and you're integrating with respect to the same variable. So g of x minus f of x, I think we worked that out just a second ago, didn't we? It was x to the 4 over 24. And then we've got the integral of from 0 to x h of t dt. Not too sure about that, so I'm just going to write it down again. But this one, I think we actually worked out this. This is simply, we actually integrated it earlier, didn't we? Look, we did it up there. It's this, just like with, so it's just x. It's without the 1, basically, because you're going to get f of t. Have I got it written down clearly somewhere on my board? This is what I mean by the cognitive load in this question. It just kind of has a lot going on. Yeah, there we go. Because we know what f of t is, don't we? I've forgotten. Look, there's f of x. Yes, we know what f of t is. So when we're integrating that, we're just integrating this, which integrates to x plus x squared over 2 plus x cubed over, yeah, so on and so forth. We do need the last term. So I'm going to write that down. In fact, I've just seen another way of doing this. I'm looking at my notes. I'm like, no, let's actually write it down a bit clearer. I'm going to write it down like this, because look at that. G of x is this, and I'm trying to show that it's h of x minus f of x, and so it's going to cancel with g of x. Let me just change what I've done here. And this is what it's like, isn't it, when you're solving these questions? Sometimes suddenly you see a much easier way of writing it down. So if you look, f of t is g of x minus 1, so I'm taking away g of x minus 1. Yeah. Well, the g of x's are going to cancel here, aren't they? And you're going to be left with, between 0 and x, h of t dt plus 1. Oh, and I've suddenly realised I've ignored the f of x. Can I just put that back in? Little mistake there. So on this line should read, this is what my maths is always like, I'm sorry, I'm always dropping terms and suddenly thinking, oh no, I've missed that. So I've got g of x minus f of x plus the integral, yeah, and then I've just rewrite this as g of x minus 1. The g of x's cancel. We're going to be left with h of t plus 1 minus f of x. And remember, we're trying to turn it into h of x minus f of x. But hang on a second, isn't this the definition of h of x which we were given earlier? Let's have a look. Were we given a definition of h of x? Yeah, h of x is 1 plus 0 to x h of t dt. Isn't that exactly what I've got down? 0 to x h of t dt plus 1. Yeah, that is h of x. So that equals h of x minus f of x, which is the left-hand side. There's really not that much going on there. There really isn't, like, but it's one of those things where it's just like, because your results for all these terms are scattered around the page, it's really easy to just get lost in what you've written down. It helps to be an organized mathematician there, which I am not, which is a shame, but it does help if you're super organized with the way you lay out your working. I'm just going to move this down here because things are getting really busy. Okay, part 5 I didn't mind at all, but that's because I kind of like, if you get lucky on these kind of bits, you can often just look at it in the right kind of way and just see it straight away. Okay, so you're given that h of x minus f of x has a maximum value on the interval 0 to a half. Yeah, x equals x0. So that's like a maximum, the maximum value when x is stuck between 0 and a half. Explain why this is true, this weird little result. Well, as I was saying before, integration in the mat and the Tamua is often really not integration. It's often just finding areas under curves, especially, when you've got an inequality here. You're trying to show that the area under the curve for this function is definitely less than that. Well, let me just draw a picture. Right, x is going to be stuck between 0 and a half. And then if we call this function h of x minus f of x, yeah, this is like the h of x minus f of x axis, if you like, because I'm interested in the value of h of x minus f of x. Well, this has definitely got a maximum somewhere between 0 and a half. And maybe it's got, maybe it's not that simple of curve. Maybe it's doing something like this. I don't know. But it's got a maximum at x equals x0. Yeah, that's where the maximum's occurring. And when you get that maximum, obviously what will be the y coordinate will be h of x0 minus f of x0. Let me just move this up a bit. So what I'm trying to say is this is the curve y equals h of x0, h of x minus f of x. Or if you like, the axis is h of x minus f of x. But the maximum occurs, well, let's just plug in x0 into our function. Okay, once you've got that, this result is actually rather obvious. What do I mean by that? Well, let's draw a little rectangle. Yeah, the area of the rectangle is clearly a half h of x0 minus f of x0. Yeah, that's the area of the rectangle. The area underneath the curve, h of t, f of t dt from 0 up to x, well, bearing in mind x is always going to be less than a half, that area, in other words, the area under this curve, is strictly less than or equal to this area of the rectangle, isn't it? The shaded area underneath the curve is going to be less than or equal to the area of the rectangle. So I just draw a little diagram like this and say, hence, the area under the curve is less than the area of the rectangle. And I hope this kind of explanation will get me full marks. I hope so. Between x and 0, h of t minus f of t dt, that is going to have to be less than or equal to, oh, let's put this in brackets as well, less than or equal to the area of the rectangle, which is a half h of x0 minus f of x0. And it's done. Yeah. Okay, I mean, that's it. I'm just going to glance over at the mark scheme here because I've got it on the other screen. The integral is at most the length of the range of the integration times the largest value of an integrand. I can see why you don't like that answer, like the way it's explained. But it does make perfect sense, though. But yeah, I understand sometimes. I've heard a few people comment under my videos that the mark schemes are really hard to understand. Yeah, you're better off with a picture here, aren't you? The picture says it all. It really does, and it looks like really complicated maths, but it's really just saying area under the curve is less than rectangle. Okay, so let's try the last bit. Now, disappointingly, the last bit was it was hard. I don't mind questions which are hard, but disappointingly, it was worth 5 marks. And so, actually, we've only done the easier bits of the question now, and now we move on to the harder bit. It's not impossible by any means, and when you see it, it looks rather obvious, but it's quite difficult. So, what are we going to do on this last bit? Well, first thing I'm going to note. I want to show obviously that f is a good approximation to h, yeah, and I'm probably going to end up using a lot of the results which I've just proved. So can I just pull down the screen so I can see some of these results? 1 second. Because, like I say, the difficult bit in this question is you get lost in all of the things that you've proved and all of the definitions of the different functions. So it's really easy to get confused here. Okay, that's better. Okay, because I think, I was looking at this and it was like, well, I'm bound to be needing some of the parts I've just used. Because, for example, if I want to show f is a good approximation to h, then I need to do h of x minus f of x. And it's better that way around because they've just told me h of x is bigger than f of x. And so that way I'm definitely going to get a positive amount and I'm not going to have to worry about the modulus. And so I started off by saying, well, okay, so h of x minus f of x, what does that equal? Well, it equals g of x minus f of x, and this is from part 4, directly from part 4 up here, plus the integral from x to 0 of h of t minus f of t dt. Now my thinking went like this. I've already established that G and F are excellent. G is an excellent approximation to F, or F, if you like, is an excellent approximation to G. Where did I prove that? There it is, says it there. F is an excellent approximation to G, which means G minus F is definitely less than or equal to 1 over 320. Yeah? And I thought, well, what about over here? I've shown that this is definitely less than or equal to a half h of x0 minus, where is it? I proved it somewhere. There it is, minus f of x0. So that's what was giving me the ideas in this question. I was like, okay, so I can make this equals an inequality because I know that this is strictly speaking less than or equal to 1 over 320, and this is strictly speaking less than or equal to a half times that. Then what I can say is, well, as that is definitely at max 1 over 320, and this is definitely at max a half like that, and this equals this, well, then that implies that h of x minus f of x, well, that's going to be less than or equal to 1 over 320, because this is, and it's equal to this. And I'll tell you what, I'll just write this down the same as before for the moment. And it's about how you lay out your working here, because I might actually change the way I'm writing this because I'm not happy with my arguments sometimes, and I like to make it clear for the examiner. So I don't want to jump too many steps in one go. I'm happy with that though. If this term, think of it like this. If you've got 7 equals 5 plus 2, which indeed it does, if you know actually that 5 isn't 5 but is like less than or equal to 5, then what you can say, well, less than or equal to 6, yeah, because 5 is less than or equal to 6, then what you can say is 7 is less than or equal to 6 plus 2. Of course you can, because 7 is less than or equal to 8. Do you see what I mean with where I'm going with that? I'm just justifying how I can just swap that in for 1 over 320. Okay, so now what have we got? We've got, well, let's take this over here. We know as x0, h of t, f of t minus f of t dt is less than or equal to a half h of x0 minus f of x0. Well, then we can deduce that if we were to, as this, if you like, let's take it over here, h of x minus f of x minus 1 over 320. As that is smaller than this, and this is smaller than that, then I can say that this is smaller than or equal to half h of x0 minus f of x0. Put the brackets in. Do you see where I'm coming from there? Hopefully you see where I'm coming from there. As this is going to be less than or equal to this, and this is less than or equal to this, I can say that is less than or equal to that. Okay, now I can rearrange. And also remember that x0, look at our graph, yeah? The maximum value of x0, h of x0 minus f of x0, that's the maximum value of h of x minus f of x, yeah? So in other words, the maximum value of this, yeah, is going to be, let's put a 1 over 320 on the other side again. It does feel like I'm just messing around with inequalities, which is exactly what this question is about. H of x0 minus f of x0. Now, why am I allowed to convert only into x0s here? Well, it's because the maximum value of h of x minus f of x is h of x0, f of x0. So if this is strictly less than or equal to this, well, I can take the maximum value then, yeah? Take maximum value h of x minus f of x, which equals h of x0, yeah? H of x0 minus f of x0, yeah? Then I can say h of x0 minus f of x0, it's going to be dead easy now, is less than or equal to, you can see why it's coming out as well, a half h of x0 minus a half f of x0. This easily rearranges into a half h of x0 minus a half f of x0 is 1 over 320, oh, less than or equal to, watch it. And now I've basically done it, but I just want to say one more thing at the end, because look at this. I've got h of x0, and I feel like I've faffed around a bit, and maybe the mark scheme is better at explaining this bit than me, probably. 2 over 320, so 1 over 160. Yeah, that's a good but not an excellent approximation, isn't it? Now, hang on a second, you might say, you're dealing with x zeros, not x's, yeah? But this is the maximum value of h of x minus f of x. Yeah, that's the maximum value. So definitely, write it down like this: as h of x minus f of x is less than or equal to h of x 0 minus f of x 0, which is less than or equal to 1 over 160, we can see clearly that h of x minus f of x is less than or equal to 1 over 160. And so it's a good but not an excellent approximation. Hopefully they'll give me plenty of the marks there, but essentially it just comes from the two results you've just proved. The tricky bit is actually recognizing that you can switch h of x minus f of x for h of x 0 minus f of x 0 because that is the largest value of h of x minus f of x. That's essentially the trick. Okay, hope you enjoyed that and it was useful. That's the main thing. I'll try and do the last couple of questions from 2015. I've got one from 2014 I just haven't bothered doing yet, and I've got the long ones from 2010. I don't know actually. You probably are more aware of what answers are available online. Let me know if there's other ones you want me to do, and if you've run out of questions to do the old step ones. I think they're really good practice. They're not exactly the same style as Matt, but the old step ones will, at least they're long questions, and I find most people anyway get quite happy with the shorter questions. If you want to practice those though, Maths Challenge questions, last couple of questions on UKMT Maths Challenge 24 and 25, Tamua questions, the last 10 would be good to do for that. But yeah, for these longer questions, I suggest step one. And maybe you find some other places. Let me know in the comments if you think you've found some other good questions, a source of good questions which are similar to math questions. Anyway, good luck in the exam. Bye bye.